Problem 7. Mr. Rose on his unicycle. And I'm sure Mr. Rose rode a unicycle when he was a kid, and they would, go to the cinema and get a sarsaparilla to drink, and now I'm just making fun of how old he is, and you guys probably don't even get the jokes. Alright, so anyway, Mr. Rose is riding the unicycle past me, and I'm sitting on a bench. Rose rides by at this constant speed. There's a small light mounted on the rim of the wheel. It traces out a path in my vision called a cycloid. And so a cycloid is this shape, and I don't know how visible or how easy this was to see on the sheet, but it sort of goes like that, and then down, and then up, and then down. So when the part of the wheel near the bike touches the ground, it sort of does that, and then it goes zhoo, zhoo. And if you look at this, if you actually, get something that rolls and put a little piece of tape on one side and then just roll it along, you'll see that in fact it's slowest here, and here and here, and fastest up here. Okay? And but we need to sort of prove that, right? So it's a relative motion problem. So think about how the light moves from Mr. Rose's point of view first. Excellent. So the way I like to think of this is, let's say Mr. Rose is riding along at a speed of v, of Rose with respect to ground. Okay, so his velocity with respect to the ground is just going to be that vrg times I hat, but really it's just going to be horizontal. Okay, there's vrg. Okay, now imagine instead of being on the ground, Mr. Rose is riding his unicycle on a treadmill, and the treadmill is going running at a speed of vrg. So that means that the unicycle just stays stationary and the wheel rotates. Okay, so the surface of the treadmill, whatever you call it, the rollers, roll this way, so the conveyor belt part just moves this way, and the wheel goes round and round and round and round and round. Okay, so how fast is a point on the edge of the wheel moving? Well, think about this. When the wheel comes down, or when this light part comes down and touches the conveyor belt, it has to be moving at the same speed as the conveyor belt, right? So when the light is at the bottom of the wheel, then relative to the center of the wheel, it must be moving that way at a speed of vrg. Okay, which means then if and the thing is that the point with the light on it is not special. This is not a special point. Every point should behave like this, which means when the light is up here, another point opposite the light should be going at vrg to the left, which means that the light should be going at vrg to the right. So what you can see is that the speed of the light with respect to the wheel, to the center of the wheel, is the same as the speed of the wheel with respect to the ground. So what I mean is that speed of the light with respect to the wheel is equal to the speed of the wheel with respect to the ground. I said Rose with respect to the ground, but whatever. Okay, so yeah, okay, anyway, forget that. So these are the same. Now these are just speeds, they're not direction, they're not velocities, right? There's no direction to them. So let's say now here is so point being, velocity of the light with respect to the wheel is not always equal to the velocity of the wheel with respect to the ground. Okay, so what you have to do now is say, okay, velocity of the light with respect to the ground is velocity of the light with respect to the wheel plus velocity of the wheel with respect to the ground. Okay, and then we want to find VLG. It's a vector sum of VLW and VWG, which are both the same length, right, because of this. So this vector and this vector are the same length, but VLW, okay, VWG always points to one direction, or let's say to the right, okay, because the wheel is always rolling in that direction. VLW changes direction, so when the light is here, it's going down. When the light is here, it's going that way. When the light is here, it's going up. When the light is here, it's going that way. Okay? So let us move down a tad. And what we want to do now is we want to show, and I'm going to make this sort of crystal clear here. So I want to do velocity of light with respect to the ground equals, and I'm going to do velocity of light with respect to the wheel in red and velocity of wheel with respect to the ground in green. Okay, so first, velocity of wheel with respect to the ground, always this way, right? So this is velocity of wheel with respect to the ground. Now if we want to find velocity of light with respect to the ground, we need to add velocity of light with respect to the wheel to velocity of wheel with respect to the ground. And velocity of light with respect to the wheel, we just tack the tail of it onto there, but this could point in any direction. It's got the same length as this green one, right? But it could point in any direction. So this here, the circle here, represents all the places that the head of VLW could be, okay? So that's VLW. So the question was, when does it have minimum and maximum speeds, okay? And so if VLG is the sum of these two, so when VLW is here, then this is, I'm sorry, yes, this is VLG when VLW is here. When VLW is here, VLG is like this, and when VLW is going back this way, VLG is 0. So you can see from this that the smallest magnitude of velocity of light with respect to the ground is 0. So I'm going to say velocity of light with respect to the ground, magnitude of it is going to be greater than or equal to 0, and it's going to be less than or equal to 2 times velocity of the wheel, or speed of the wheel with respect to the ground. So the fastest the light could be going is twice the speed of the wheel when both vectors are pointing the same way, and the slowest it can be going is stationary when they're both pointing the opposite way. Okay, so at what points in the cycle is the light going the same way as the wheel, and at what points is it going the opposite way? Well, I don't know why I drew that. I mean, I had a reason in my head, but now it's gone. Okay, so the answer is, well, if the wheel is always going, let's see, I'll do, yeah, green for wheel, well, blue, wheel with respect to the ground. The wheel is always going this way, right, to the right. So the speed of the light with respect to the ground will be at a maximum when the light is up here, because that's when the light velocity is going this way, and it'll be at a minimum when the light's velocity is down here, because that's when the light is going that way. When it's down here, the velocity of the light with respect to the wheel cancels the velocity of the wheel with respect to the ground, and it's 0. And up here they add up, and they're both the same magnitude, so they go there twice. So that's why the light on the wheel, on the very edge of the wheel, goes the slowest when it is at the bottom of the wheel, and fastest when it's on the top, as you will see if you spend much time watching bicycles or unicycles or whatever with lights.